Section 8.4, Applications to Economics and Biology. So as I said, we're going to focus on the economics part. Now, the whole idea behind this chapter is to show you that integrals can be used in physics, they can be used in economics, they can be used in biology, they can be used in probability, like statistics stuff. We showed you how to find the arc length, like the length of an arc, using integrals. We showed you how to find the surface area of a surface using integrals. And then in chapter 9, we're going to continue showing you more applications of integrals, where we use it in differential equations. We're going to use it in Euler's method, directional fields or slope fields, and how we solve differential equations and modeling with differential equations. And then later on in chapter 10, we're going to move on to something totally different than just integrals. So what do we need to know here? So again, one application to this, because this is application, it's not like you have to explain a concept, but the application to this, which is covered mostly in business calculus, is we need to know an idea. So let's say, first thing I want to talk about is I'm going to sketch a graph there, x and b here, or y. Say we have x units of some product, okay, of some product. And p of x is the price, So say like the price that the company, or an individual has to pay or to charge in order to sell X number of units of some product. And what happens is the more you buy, the less the demand. Okay, so the more units you buy, the less demand. So that tells us that we have what we call the demand function, as represented by this curve. So the longer, the more the x, the lower the curve. And what we have here is, so this tells us that the demand function is decreasing. So this curve represents the demand function. It's going to be an decreasing function. What we need to know here is call this P or P of X. And what we're going to do is we are going to take, if we select, say, capital X units, if we project it up and then horizontally, that would be X, and then let's call this capital P like that. We define small b to represent the demand for a product. And I'm going to call capital P is the corresponding price to the given sales level. So what you see below the small p and above capital P, because that's P here. So what you see above capital P and below small p, which is the shaded region, this is called consumer surplus. It's called consumer surplus. So what is consumer surplus? the difference between the price the consumer has to pay and the price that he or she is prepared to pay. Because sometimes you might have an item for a certain price listed, some people might be interested to pay more for it. So the difference between the price the consumer has to pay and the price that the consumer is ready to pay is called consumer surplus. So what happens is, as I said, it's basically the yellow shaded region here. And how do we calculate all of this? Notice this is basically, you can interpret it as an area. And what we did back in Riemann sum, you know, we split this into rectangles like so, right? We split into rectangles with delta x. So any vertical rectangle you have, so now this distance between what you have, the bottom, any column of any rectangle, say I wanna deal with this rectangle. So this, the difference here is p of xi at some xi minus capital P, and the width of the rectangle is delta x. So in this case, if you look at the graph, what is small p of xi minus capital P? So originally you wanted to pay this much money all the way up, that much money, but then you ended up paying lower, like the bottom one. So the difference, that would be the savings per unit, right? That's how much you save. So you originally were planning to pay that much, you ended up paying less. So that difference is how much you save per unit. So we can say here, P of xi minus capital P is the savings per unit. And delta x is going to represent the number of units. When I multiply them together, P of xi minus capital P times delta x, that basically gives me the area of one rectangle. If I sum this up from I equals 1 to n over n rectangles, that will give me the sum of the areas below for n rectangles. And when I take the limit of this as n approaches infinity, that would give me the consumer surplus, right? The consumer surplus, the whole yellow thing. Another way to do this, instead of doing Riemann sum, we can do the integral, right? The integral of P of xi minus capital B dx, with the integral from 0, because we are integrating over the x-axis. So if you see, we went from 0 to capital X on the graph. So we try to look at an example now. Let B equals 1000 minus 0.3 small x minus 0.002 x squared. B, the demand for a certain product. We are asked to find the consumer surplus when sales level is at $400. So that P here is capital P. Or it depends how you're gonna look at this for the meantime. So they give us the 400. This sales level is 400. That's the X value, which on the graph we represented by capital X, by this. That's the 400. So if I want to find what capital P is, I just plug that into the given P of X demand function to get the corresponding P value. So that's a small p here, P of X, is given as again 1000 minus 0.3x minus 0.002x squared. So I want to first find P of 400. That's 1000 minus 0.3 times 400 minus 0.002, 400 squared. And I'm sure everyone can calculate this. This will give me the capital B value, which I got 660. Then the consumer surplus is the integral. Remember, we're integrating over the x-axis. If you remember, the yellow region was from 0 to capital X. So 0 to 400. P of X, small p of X, which is the given function, 1000 minus 0.3x minus 0.002x squared minus 660 dx. And you can combine these together, 0 to 400, 1000 minus the 660, 340, minus, keep everything else the same, and then we can integrate this one. 340x minus 0.3x squared over 2 minus 0.002x cubed over 3 from 0 to 400. If you substitute the 400 in and do the work, you're going to get 208,000 over 3, which is about 69,333.33. So this means if we buy 400 for $400, the savings here will be that much based on the demand function that was given to us. Another example, again, we use this a lot in business calculus. So we have what we call the cost function. The cost function C of X. If I find the derivative for that, that will give me what we call the marginal cost function. And then we have more, we have the revenue. Revenue is, we use capital R for that, is X times P. P is the price. X is the number of items. That gives you, like if you're selling, you buy like 10 markers. On each marker, you bought it for $2, right? You're gonna sell it for $5. So what happened? You want to find the revenue. Revenue is how much you're gonna sell it for. And then if we take the revenue minus the cost, that will give us the profit. If you find R prime of X, if you take the revenue and you square it, find the derivative, that's called marginal revenue. Now, how do we apply all this to integrals? We introduce what we call the net change theorem. That was covered in Calc 1. The net change theorem said but as an application, when a changing quantity Q of t changes by a rate R of t, the net change of the quantity during the interval from A to B is given by Q of B minus Q of A equals the integral from A to B of R of t dt. That's called the net change theorem. We have an example. A company estimates that the marginal revenue in dollars per unit realized by selling X units of a product is modeled by this function 48 minus 0.0012x. Find the increase in revenue if sales increases from 5,000 units to 10,000 units. So, by the net change theorem, we can say we're going from A to B, that's from 1,000 to 5,000 to 10,000. So we say R of 10,000 minus R of 5,000 equals the integral from A to B, again from 5,000 to 10,000, times the given function 48 minus 0.0012x. So if we integrate this, 48x minus 0.0012x squared over 2 from 5,000 to 10,000. And then when you do the calculations, we got 195,000. Note for number 7 on the homework, try to go over or read number 6. Why? Before you do number 7. It talks about what we call producer surplus. That's when you're selling for cheaper price.